through these following topics. First, we'll touch upon how cross data center replication works in Espresso and how Espresso achieves eventual consistency. Next, we will understand how inconsistencies are discovered. Then we'll discuss what are the actions required to fix these inconsistencies and how they are executed. And lastly, we'll talk about some statistics, challenges, and future work in this area. So let's touch upon some important aspects about Espresso's architecture that are relevant to today's discussion. Within a data center, every Espresso database is divided into multiple partitions, and every Espresso partition has a leader and two followers. The partitions themselves are distributed across multiple machines. Every database is also replicated to multiple data centers. Thus, Espresso does two kinds of replication. One is within the data center, which is between a leader and its follower partitions, as well as cross data center replication, which is required to keep two copies of data in two different data centers in sync with each other. So cross data center replication in Espresso is active-active. So each Espresso database is replicated to multiple data centers that reside in distinct geographic locations. And the record that lands on any data center is replicated to all other data centers. Now, since a user can write to any of these data centers, it is possible that at a given instant, before replication is complete, two different data centers may hold different values for the same key. But once replication is complete, Espresso will reach eventual consistency. So in order to understand how Espresso achieves eventual consistency, it is important to understand last writer wins. Now, to put it very simply, last writer wins means that the write with the lower timestamp is discarded and the write with the higher timestamp is persistent. So let's see an example to see how this works. We will consider two users who are writing a record for the same key color in two different data centers at timestamps that are close to each other. But the first timestamp is smaller than the second one by a few milliseconds. Now, user A is trying to write the value blue, and user B is trying to write the value green. Now, as we discussed, record that lands on each data center will be replicated to all other data centers. And the decision for which writes to retain and which writes to discard is made independently by every Espresso store by following a fixed set of rules. So let's see what happens next. Record that lands on data center 1 will be replicated to 2. Now the Espresso store in data center 2 will see that the timestamp of this incoming write is lower than the write that exists locally, and it will discard the replicated write according to the last writer wins rule. At the same time, the record that lands on data center 2 is replicated to data center 1. And Espresso store in data center 1 observes that the timestamp of the incoming write is higher than the local write. So it will accept it based on last writer wins. Eventually, we see that both data center 1 and 2 will agree that the correct value for the key color is green, and the record becomes eventually consistent. When these timestamps match, the tie is broken by data center priority. So now that we understand how Espresso becomes consistent, let us also look at how we can end up with an inconsistency. So let's go back to our earlier example, where the record with key color and value green was replicated from data center 2 to 1 successfully. Now let us assume that for whatever reason, that replication did not go through. Right? We would then be left with two different values for the same key color, and the record would be inconsistent. So cross data center inconsistency can happen because of site issues in the underlying replication infrastructure, Kafka, or the occasional code bugs which impact rare corner cases. But an important thing to note here is that the total number of such inconsistencies is small. If we look at all the inconsistencies that we have discovered since the beginning of Espresso, they are about 0.004% of the total records in Espresso. But our goal here is to prevent these inconsistencies from becoming permanent by proactively finding and fixing them. So there are multiple ways to improve consistency. So we will look at how Espresso applies some of them. First, to quickly catch serious bugs in our replication system, we have an online consistency check mechanism. Here we will validate a sample of rows that are changed by the most recent writes. This will not capture all the inconsistencies, but it will catch serious code bugs in a short period of time. Next, we have our offline check and fix mechanism. Here we will scan and fix all data, and it's a catch-all mechanism, but it will take much longer to catch and fix these inconsistencies via this route, simply because of the volume of data that you're scanning and fixing. And lastly, we continue to improve our systems to handle failure gracefully, fix code bugs, and prevent data loss in case of ungraceful failure. For today's session specifically, we are going to take a deep dive into the offline check and fix mechanism and look at how it provides the eventual consistency guarantee. So let's look at how this mechanism works on a very high level. The process is logically divided into 3 stages. So the first one is comparison, next decision, and fix. We have a data validation service which will schedule each of these stages for a database. The comparison stage, as the name suggests, will compare data from 2 data centers and find all inconsistent records. The comparisons are done two-way, and the last right of win comparisons are transitive. The next is the decision stage, where based on the result of comparison, it is determined what is a good end state for an inconsistent record and what is the action needed to take it to that stage. The last stage is fix, where the action determined to fix the record in the decision stage is applied to the Espresso store. So let's talk about comparison. That is the first stage in a little more detail. So data files that you see here, they are snapshots of Espresso data at a particular point in time. Now the data validation service will first compare the checksums of files from 2 data centers. Only if those checksums don't match, it will then fetch the data file and scan and compare it record by record. The discovered inconsistencies are then divided into several categories based on their nature, which is helpful for the following stages. So now Mengjin will take over from this point and explain which metadata we use for this comparison.
Yeah. So thanks, Radhika. And so in the comparison step, when the data file checksum comparison fails, how do we compare the records in the data files from the 2 data centers? To understand the mechanism, we'll need to first take a look at what the data files look like. So the data files that Espresso uses to detect the inconsistencies contains extracted metadata for each of the records. So this includes the record key, the timestamp, the checksum of the value of the record, and the status, which indicate whether the record is deleted or not, and origin data center, which indicates where the write action originally come from. And on the right side, you can see a simplified example of what a metadata record will look like. Now we understand the data file. We can then take a look at how those metadata are used to compare the records and how we can decide on the correct end state of the record. As there will be so many different cases, let's look at the following case as an example. So in data center 1, we have a deleted row, and the delete action originated from data center 3. At the same time, in data center 2, for the same row, it is actually an active row, and the write action happened locally. Now we have an inconsistency. To determine the end state, we'll need to leverage the last right of win policy that we introduced earlier in the talk. We need to compare the timestamp of the 2 records. And by looking at the 2 timestamps, we know that timestamp for data center 1 is actually larger. So we can conclude that the record in data center 1 should be the end state. Until now, we have detected the inconsistency and we have the end state of the record. But then how we can fix those inconsistencies? To fix inconsistencies, Espresso uses a special kind of request, a touch request. Let's go back to our earlier example where we had an inconsistency because the record from data center 2 did not reach data center 1. So both data centers hold a different value for the same key. A touch request can help us in this case. A touch request is like its name. It touches a record in Espresso, replays the record to the replication pipeline, and the corresponding event goes into the replication pipeline as if it was just written, but with timestamp of original write. Back to our example. If we send the touch request to data center 2, the record will be replayed to data center 1, which wins based on last Friday win policy. And the view now is consistent for the same key. With understanding of how the touch request works, let us now try to fix the inconsistency we detected in the comparison step. In the previous comparison, we know that data center 1 contains the end state of the record, and the data center 3 is the original data center of the delete action. So in this case, we'll send a touch request to the origin data center so that the delete action can be replicated again with the original delete timestamp. With this, the delete action replicated to data center 2, and based on the last Friday win policy, the delete action actually wins. And now the view is consistent and the consistency is fixed. So now we understand the fixing mechanism. Let's go back to look at the pipeline setup for the decision and fix step. Here we have an end-to-end diagram of the whole process. And in the decision and fix step, we'll have two modes, the online mode and the bulk load mode. The online mode will first determine the actions or requests to take, and then directly apply the actions to the Espresso services through online traffic. At the same time, in bulk load mode, instead of applying the request or actions directly to the Espresso services, we'll first write those requests to an offline data store. And then we'll leverage our bulk data loader framework to read the requests from the data store and apply the request to the Espresso services in an offline manner. And here we listed some comparison points of the two modes on the left. Now we're clear on the pipeline. Let's look at some data. Until from the beginning, we've already successfully fixed around 0.004% of all of our records. But need to notice that those records include the historically accumulated differences and differences from previous outages. And within the system, it'll take us around 2 days to scan and fix all of our hundreds of databases. And on the monitoring front, every day we'll send report to show the inconsistency status so that the potential issues can be surfaced to our team member. So those stats are great, but we're not done yet. During operating and maintaining the system, we discover there are challenges for us to further improve. In our previous experiences, we find that in the current two-way comparison model, it could be hard to determine the end state with the information from only 2 data centers. And thus, it could take multiple compares for some differences to be fully fixed. And below is an example of this case. In this example, it'll take 2 rounds to fully fix the inconsistency for a single record between 3 data centers. To solve this challenge, we plan to work on an n-way check and fix mechanism by using MapReduce. The mechanism will pull in data files from multiple data centers, compare and patch based on information from all the data files. And with this mechanism, from the example on the previous page, the end state can be achieved within 1 round of comparison and fix. On a related note, another form of consistency check within Espresso is for materialized view. I will just touch upon very briefly here. Materialized views were originally created because multiple teams had to access similar data sets with just different partition keys. And for example, we have table 1 and table 2 here. And table 2 is just a mapping from table 1. In this case, we call table 2 view table and table 1 primary table. The view table is derived from the primary table, and materialized view can auto-populate view table based on user-defined mapping. And it is through a pipeline that's very similar to our replication pipeline. And that's inconsistency between primary and view table can happen due to issues in the pipeline. Therefore, Espresso built materialized view recovery mechanism so that to check and fix inconsistencies between primary and view table with similar manner as we check and fix cross-Colo inconsistencies. And that's all of our talk. Thanks for listening. Now back to Matt.
Thanks so much, Radhika and Mengjin. That was great. It's awesome to look into some of the details that go into replication and how do we handle sometimes when replication goes wrong. Our next talk is about Ambry, and I'd like to invite up Ankur.
Hello, everyone. I hope everyone is having a great day so far. My name is Ankur. I work for Ambry, which is a geo-replicated active-active blob storage system of LinkedIn. And today we are going to talk about some of the disaster recovery efforts and the disaster recovery project that we built for Ambry. So let's get started. All right, so let's get started. We are going to start with a brief discussion about why a separate disaster recovery solution was needed. We ended up using Azure as the location to backup. I'm going to briefly touch upon a few points about why we chose Azure. Then I'm going to delve into the overall architecture of the solution. And finally, if we have enough time, I'm going to talk about some of the challenges due to inconsistencies and some impedance mismatches between Azure offerings and Ambry. So why did we decide to build disaster recovery? Ambry, after all, as I mentioned earlier, is a geo-replicated active-active blob storage platform. That means we already replicate data across data centers in different geographical regions. Shouldn't that be enough to help us with any disaster? Well, for many disaster models, that indeed is enough. But our disaster model for this project is a little different. We are worried about tooling or rogue access that can accidentally or maliciously corrupt data across all replicas. It also helps with some other needs of LinkedIn. LinkedIn being a social media, data and metadata backed up to tamper-proof location with restricted access helps with security and compliance. Obviously, a disaster recovery solution helps us with business continuity. This solution that we built helps create a dark backup that is managed by different personnel other than the main cluster. And hence, it helps create an isolated environment that cannot otherwise be accessed. And finally, it helps us create a verifiable recovery flow that can be verified and validated on a continuous basis. Now let's look at why did we pick Azure. Well, Azure is an external system, and Ambry tooling doesn't have access to Azure. So this provides us the isolation that we were looking for. Azure has a lot of other services that can help with encryption and other stuff. Azure provides flexible access control lists to help us control and access and restrict access to our backed up data. And finally, if we have data in Azure, then in future, we can leverage that to serve data from Azure. All right, so having gone through some of the motivation, let's look at the architecture. Overall, as I described earlier, Ambry is a geo-replicated distributed system that replicates data across multiple geographically separate data centers. So that means we already have a replication layer that helps us move data across data centers. In order to build the disaster recovery solution, we just reused and extended Ambry's replication protocol, which I'm going to describe in more detail in the next slides. So first, let's look at the Ambry replication logic. Ambry divides its data into multiple logical partitions. Each partition has some replica within the same data center and some in remote data centers. Blobs can be served from any data center. We have an active-active model. In the example diagram shown here on the left, we have 3 data centers and 3 replicas of a partition in each data center, the color boxes being the replicas of a partition. These three data centers are, of course, geographically separate. Within a data center, the local replicas all replicate with each other. Ambry's replication layer has the capability for all replicas, whether they are remote or local, to be able to replicate with each other. Or Ambry's replication protocol can also define a leader in each data center, such that cross data center replication happens only via the leader to save cross data center network bandwidth. Within each replica itself, the data is stored in an append-only storage abstraction called log. The replication protocol's job then is to make sure that each replica's logs are up to date with each other. In order for any replication to work, we need two things. We need a reliable, replayable, ordered log of changes from each replica so that none of the changes are missed. Note that, as we will describe in this example later, the ordering of data in different replicas can be different. But within one replica, the ordering should be reliable, replayable, and consistent. And the next thing we need is a concept of a reliable replication token, which is a marker in this ordered log of changes, representing the point up to which the replicas are in sync with each other. For a log-based storage like Ambry, simply an offset in the logical file can act as the replication token. Now, enough for the, let's consider an example, which we have shown on the right, where we have replica B, which is replicating from replica A. And these two could be cross data center replicas or local replica. It doesn't really matter as far as replication is concerned. In this example, replica B has caught up with replica A till the offset K in its log. So the replication token here is K. As shown in the figure, a replication loop has the following steps. First, replica B sends a request to replica A asking for the list of blob IDs after its replication token for replica A. We call this step replica metadata request. Replica A looks at its local log and sends back the blob IDs in its log after the offset K. We call this the replica metadata response. Replica B then checks its local data and determines the list of missing blobs. In our examples, between these two replicas, the missing blob IDs are 1, 8, and 5. It requests replica A for the data of these missing blob IDs. Replica A then responds back with the requested data. And finally, replica B writes the data in its log and updates new offset up to which it has caught up with replica A. That is its new replication token for replica A, which in our case is now K dash. Now do note, as I mentioned earlier, both these replica now contain the same set of data, but their ordering is different, which is fine as far as replication is concerned. Now let's see how to extend this solution for disaster recovery. Well, I already spilled the beans earlier. We are going to use replication. So the solution seems simple. Just add Azure as the 4th data center, replicate with Azure. But we are all engineers here, and we know that the devil lies in the details. Where do we store this data? Do we store this in Azure Managed Disk, in transient disk? Azure provides a blob storage solution called Azure Blob Storage. Looks like that might be a good fit. After all, both Ambry and Azure Blob Storage store blobs. But how do we replicate against Azure Blob Storage? As I described in so much detail in the previous slide, for replication, we need a replayable ordered log of changes. How do we get that for Azure Blob Storage? And how do we maintain a replication token? There are other concerns too. The replication logic, as we saw before, needs someone to run the replication loop and respond to the replication events. Additionally, we need a reliable, high bandwidth network connection between LinkedIn data center and a public cloud like Azure so that our replication can make sufficient progress. All right, so let's look at each of these concerns one by one. In order to respond to replication requests, we create a cluster of stateless nodes in LinkedIn data center that bridge the replication between Ambry and Azure. We call them VCR, the virtual cloud replica. The VCR has 3 responsibilities primarily: to run the replication loop for backup, to respond to replication queries or requests during recovery, and to perform compaction on the backed up data. Note that VCR cluster is in one of the LinkedIn data centers that is geographically closest to the Azure data center where we back up the data. Moving on, how do we talk to a public cloud on a reliable network with bandwidth high enough to ensure that replication makes fast enough progress? Well, we use ExpressRoute, between LinkedIn's data center and the Azure data center for that. Finally, where do we store the backup? We use a combination of Azure Blob Store and Cosmos DB. We store the actual blob data and replication tokens on Azure Blob Store, while we store the metadata on Cosmos DB. Now this begs a question. Azure Blob Store should be enough to store the blobs. Why do we need the Cosmos DB? Well, Cosmos DB is the magic that helps us with replication. It provides change feed for each partition, which we can use for the ordered replication log that we need for replication. It provides other benefits too. We can store rich metadata for each blob in Cosmos DB, which can be used to do flexible queries, which wasn't earlier possible. Cosmos DB allows us to index any number of metadata fields for faster access. But as you might guess, introducing another data system comes with its own challenges, like consistency issues and partial failures. Blobs could be written to Azure Blob Storage, while metadata update for the same blob to Cosmos DB might fail, and vice versa. Adding another data system adds additional latency for updates, and of course, it adds more cost and complexity. Additionally, Cosmos DB throttles queries, especially queries that access large amounts of data very aggressively, even when requests are within quota. We had to design our replication to work around this limitation. Finally, there was an interesting issue due to impedance mismatch between Ambry's replication logic and Cosmos change feed. I'm going to talk about it in the later slides. Note that there are numerous other challenges. There were actually numerous other challenges with the overall solution, like ordering of updates between Azure Blob Storage and Cosmos DB, both during backup and recovery, the request rate, throttling, data consistency related challenges, to name a few. I'm going to gloss over most of them today in the interest of time, but time permitting, I'll talk about this impedance mismatch for replication in later slides. But before that, let's tie up everything together. Here's how the backup architecture looks like. VCR runs the replication loop for backup. In each partition, it gets the replica tokens from Azure Blob Store and asks for next set of blobs from Ambry replicas, the step that we earlier called replica metadata request. Ambry replica responds with the next set of blobs, the replica metadata response, and VCR then checks Cosmos DB to identify missing blob IDs in the set. Finally, VCR requests for the missing blobs data from Ambry replicas and stores the blobs in Azure Blob Storage and the metadata for those blobs in the Cosmos DB. Now let's take a quick look on the compaction. VCR periodically queries the Cosmos DB for blobs that need to be compacted away, and then deletes them both from Cosmos DB as well as Azure Blob Storage. And finally, let's look at the other side of this, recovery. During recovery, the data flow gets reversed. Ambry replicas run the replication loop and replicate from the backed up data in Azure. In the replication loop, Ambry replicas asks for the next set of blob IDs from VCR after a replication token. This is the replica metadata request step. VCR queries the Cosmos DB and returns the next set of blob IDs after the token. Ambry replica then checks its local store to identify the missing blob IDs and requests VCR for the missing blobs. Next, VCR gets the missing blobs from Azure Blob Store and returns them back to Ambry replica. Finally, the Ambry replica writes data to its local store and updates its replication token. Things look simple at this stage, and the recovery problem looks solved. Well, not yet. As I alluded to before, there is an impedance mismatch between Ambry's replication logic and Cosmos DB's change feed. The problem is that there is a difference between how Ambry's replication layer expects replication requests and responses to be, and how the Cosmos change feed API behaves. As promised, let's look at it in slightly more detail next. This is an example of Ambry replicas pulling data from VCR node during recovery. As we have noted multiple times so far, a typical replication request starts with Ambry replica asking for the next set of blobs after replication token. Let's call it S, it being the start of the loop. The replication loop should then make progress by returning the next set of blobs. But how many blobs? Note that the amount of exchange data in each replication request needs to be limited. Otherwise, we risk timeouts and network saturation due to replication. So Ambry replication logic limits the size of the data that can be exchanged in each replication request. In our example, Ambry replica asks for the next set of blobs after replication token S, but limits the size of the data exchange in replication to 4 MB, meaning return of blobs up to a max cumulative size of 4 MB. But this is not how Cosmos change feed API behaves. It limits data by number of items instead of any size. So the change feed request looks like, give me the next set of blobs after replication token S up to a max of n items. In our example, it is 10 items. The change feed API returns the list of items and returns a token E. E here stands for since this is the end of replication loop. And so it returns a replication token E, which can then be used as the next replication token, but only after all these 10 items are consumed. There are no tokens for partial consumption of items. Can this lead to any trouble? Turns out it can. It's possible, as you see in the diagram, that the size limit requested by Ambry replica is reached with fewer number of blobs. In this case, even if VCR exchanges the side limited items during replication, the Ambry replica cannot move its token forward to E because the whole batch wasn't consumed and we don't have token for partial consumption. Since the token cannot be advanced, the next replication cycle should continue with the same token S and get stuck in a loop now. So how do we solve this problem? Well, we introduced a cache of change feed data in VCR. The VCR responds to replication requests from Ambry replica using this cache and makes sure that the cache remains up to date by issuing queries to change feed API as needed. The replication token also changes slightly now. Instead of earlier just being the continuation token, which is what Cosmos DB change feed API returns, it now includes the start token, end token, and index of the items between these two tokens, and also a cache cookie to help us with cache consistency and failure recovery related issues. So this is how the final replication solution looks like during recovery. VCR queries for a configurable number of items in each change feed request and then caches it. Ambry data nodes query VCR for replica metadata, the next set of blobs. The VCR looks up in its cache to respond, and it takes care of keeping the cache up to date by issuing additional change feed queries to Cosmos DB as needed. All right, so that's all about the architecture and challenges. In the end, let's look at some of the numbers real quick. One Ambry cluster has over 10,000 partitions and petabytes of data with tens of billions of blobs of varying sizes. And this is just one of the Ambry cluster. This is our scale. The backup and recovery of multiple partitions can progress in parallel, which is great. But our main bottleneck for the solution is bandwidth. So as we increase the network bandwidth, we get better performances for the system. And an important thing to note is, even when the system is under recovery, even if we are recovering because of a failure or corrupted data, the system is still writable. And with VCR, we also have the option, we also have the potential to serve reads during the recovery. So that concludes this presentation. A big shout out to all of my fellow teammates for taking on this massive effort. Feel free to reach out to any of us if you have additional questions. And of course, we are going to be here to answer any questions later today. Thanks everyone for tuning in. And now it's over to you, Matt.
Thank you so much, Ankur. Great presentation, diving deep on Ambry's replication and disaster recovery. It's a topic that's dear to my heart. Our next presenter is from the Venice and DaVinci team. I'd like to bring on stage Alexei.
Welcome, everyone. My name is Alexei. I'm from Venice team, and today I'd like to talk about our new embedded key value storage that we built. Let's share the slides. Okay. Today, talk about motivation for this project, some implementation details, key features, and a short summary and results. So first of all, some might have a question, what is the derived data? And simply, it's a data that's not source of truth. In other words, it's computed from some base data. And typically, there are two sources of derived data: nearline, all kinds of streaming processors, and offline, which is typically Hadoop. And some examples of derived data are search indexes, AI model features, or data of recommendation systems, for example, people you may know. And although DaVinci and Venice don't make explicit assumptions about source of the data, it has been specifically designed and optimized to work well with derived data. Okay. On a regular basis, Venice team works with many other teams and try to consult them, and noticed a growing demand for a key value store, which is primarily driven by the need of arbitrary computation that is collocated with the data. It was one of the motivations for the project. Also, we wanted to improve velocity of AI teams by decoupling model and feature deployment. Also, having reliable and consistent performance is challenging for any multi-tenant distributed system because of noisy neighbors. And we wanted to serve such use cases that are affected by this problem more efficiently. And finally, one of the search verticals had performance issues, and introduction of more modern and flexible key value store could solve it. So we believe that it could solve it. So briefly, what is Venice? Venice is a well-established, eventually consistent distributed key value store. It's built based on Lambda architecture. So what matters for the sake of this presentation is that it's a distributed remote system. It's eventually consistent. It's multi-tenant. And Venice is a well-established system among LinkedIn's AI teams and is a natural first choice for many of them. But remote multi-tenancy doesn't always meet performance requirements. And here are a few use cases that's quite difficult to serve. One is when application access data in high bursts. It's difficult because Venice uses quota managed access, and it's difficult to assign a meaningful quota for such an application in an efficient way. Also, another use case is when application requires sub-millisecond access. And Venice, being a remote system, cannot always meet this requirement. I want to say that Venice team was able to alleviate some of these issues in many cases by building dedicated clusters. However, it is expensive, time-consuming, and at the end, is not always practical. Okay, so what is a DaVinci in a few words? It's a durable, remotely populated, embedded key value store. So why do we want it to be durable? Because application nodes become stateful, and by making DaVinci durable, we improve bootstrap speed and reduce service downtime, which is very important for us. Why do we want it to be remotely populated? To decouple data producers from data consumers and improve operability by providing centralized management interface. And finally, why does it need to be embedded? To guarantee predictably high performance by moving data closer to computation nodes and avoiding neighbor noise. So DaVinci, we built DaVinci as a new stateful client for Venice that targets these challenging use cases and offers embedded class performance. Here are some reasons why we decided to leverage DaVinci. Leverage Venice. Venice contains many data sets useful for AI applications, and we thought that it would be great to make this data available for other applications that weren't able to use Venice before due to performance requirements. Also, Venice built a very robust and performant data delivery pipeline that we would like to leverage and reuse. And here you see like a very small picture of how DaVinci fits in the Venice world. Basically, we have some stateless classical Venice use cases when applications use Venice Sync client, doesn't have any state, and access data from Venice. And we also have a new type of use cases, stateful applications that use DaVinci client, and DaVinci client internally manages state. And we build DaVinci client in such a way that it's interface-wise compatible with Venice classical client, so it's easier to onboard, to make it easier to onboard. And when we started building it, we set a list of goals for MVP, and here's some of them. So we wanted to have a minimal impact on application environments because we wanted to solve performance issues and not introduce new ones. We also wanted to support transparent schema evolution to improve experimentation velocity and let people publish new data without redeploying the code, for example. We also want to make dataset replacement transparent to applications, so it's easier to integrate, and application doesn't have to be redeployed when data is being changed. And finally, we wanted to serve wide range of dataset sizes from hundreds of megabytes to terabytes. And huge datasets doesn't fit on a single node, so they have to be partitioned. And DaVinci has to let application to control how datasets are partitioned to ensure that data is collocated with application shards. Okay, so here's a very simplified view of what we had in the beginning, how Venice looks like. And I won't go into details, but if you're interested in Venice, please check our presentation from previous years because Venice team presented it. But what's important is that Venice is a distributed system. It's pretty complex. It has many components, and the logic that we put in a DaVinci client kind of spread across several components: Venice routers, controllers, but mostly Venice server. Also, Venice has multiple clusters which are transparent to a classical client, but DaVinci client has to be aware of them, right? And also Venice, because it's a service, it has many external dependencies as well. And we wanted to create DaVinci as a library. And library, it's difficult to ensure that all our users use a latest version of a library. So we need to be mindful about all dependencies that we put in the library. So that's what we've done for DaVinci. So how DaVinci works? It's eagerly downloads data from Venice Kafka cluster and stores it locally on the application node. In Venice architecture, DaVinci acts as a follower and listens to all relevant updates to keep the local state in up-to-date state. So the queries can be served from the local state without incurring the cost of accessing over the network. Queries can be served from either memory or local disk, but in either case, local state is always persisted. And we build DaVinci in such a way that it's not only can be used directly, but it can be used as a building block for providing more complex and specialized infrastructure. For example, different applications has very different partitioning scheme. So some applications use very high replication factor, some use very high or low partition count. And we wanted to support all of them. So we decided to let applications define how they want to do that. What means that application, for example, can combine can use Helix or any other cluster management system combined with DaVinci. Because DaVinci does not restrict how many partitions or replication factor can be used. Okay. So here's how we achieved our design goals. Now, to have minimal impact on application environment, we isolated bulk ingestion in a helper JVM, which helped reduce garbage collection pressure on application JVM. We also aggressively reused objects throughout the read path, further reducing garbage collection pressure. To reduce number of dependencies and hide a lot of complexity related to multi-cluster setup, we leverage DaVinci internally for metadata access. We created a new metadata stores using Venice, leveraging Venice, that's accessed using DaVinci. So access is fast and it's completely hidden from the application. We also made a number of optimizations in FastAvro library, mostly around promoting lazy deserialization and direct array access. So if application doesn't use a certain field, in some cases, we won't even deserialize it. And for arrays, in some cases, we can access array elements without deserializing the payload. We can access directly. All of it greatly reduced garbage collection pressure on application JVM. To support transparent schema changes, we leverage Avro, and it helped us to decouple readers and writers. We also ensured that schema changes are backward and forward compatible. It lets users publish new data sets without upgrading existing applications that's running in production. And if mistake is made, data sets can be reverted without crashing those applications. We also assume that application nodes are serving online traffic most of the time. So we want it to be scalable, and we want to replace data without bringing a node out of the cluster. And to ensure that it's possible, our read paths and ingestion paths are not synchronizing. And to do that, we applied concurrent reference counting to dataset versions. And we also ensure that stale versions are deleted outside of read paths. Okay. And to support application-defined partitioning schemes, we let users register custom partitioners. They can specify how many partitions they want and how to map keys into partitions. But it created one problem, that previously partitions, Venice had a full control over a number of partitions, and we can use it to scale better, right? But now we expose number of partitions to users. So to decouple it, we introduced a scaling factor. So, for example, user can specify a fixed number of partitions, but internally, Venice can still grow number of partitions if data size increases. Okay. So DaVinci has been successfully used in production for a little bit more than a year at this moment. And we built a lot of configurations. DaVinci offers several cost performance options to satisfy a wide range of requirements, including on-heap object cache that can be combined with either on-disk or in-memory storage backends. Okay. Yeah, that's it. Thank you.